All right, so today we're going to start getting into naming molecules and compounds. The naming systems we're going to use are pretty simple and easy to follow, but there's a lot of rules to remember, so bear with me. This article I found pretty funny. It talks about a city in California where they were worried about the potentially dangerous properties of dihydrogen monoxide, and they considered banning phone cups after they learned the chemical was used in their production. Then they learned to their chagrin that dihydrogen monoxide, H2O for short, is the scientific term for water. This happens on a yearly basis with these towns all across the United States because they don't have anybody working there that took a basic chemistry course. My favorite one was, I think there was a town also in California where they said dihydrogen monoxide is dangerous. If you inhale it, you will die. It's like, yeah, you're describing drowning, great. It doesn't mean it's that dangerous, right? So knowing how to name molecules is really important. Oftentimes we have common names. So in this case, the common name for H2O is water, but the scientific name is actually called dihydrogen monoxide. So we've got to get into the naming system for scientific naming. And in order to do this, we need to know some prefixes. So prefixes are used when naming covalent compounds. How do we know if a molecule contains a covalent compound? Or a covalent bond, I should say. Yep.
It has two nonmetals?
Yeah, it's normally between two nonmetals. And the electrons are shared. So that's an important thing to remember. This system is only useful for naming molecules that can contain covalent bonds. So let's take a look at some prefixes. And then the number that they represent. And then we'll go through some examples. All right, so let's make a list of numbers here going from 1 to 10. All right, does anybody know the prefix for 1? Mono. So you can think of monocle, right? If you have that little eyepiece, that's a monocle. All right, how about for 2? Di. This one confuses people. I was laughing last year. I had a student say, well, why do we call bicycles bicycles and not dicycles? I was like, I don't know, actually. That's a good point. So di is scientifically used for 2, not bi. All right, what about 3? Tri. All right, what about 4? This is another tricky one. It's actually tetra. Again, students will say, well, why don't we call it quad? You think about like an ATV, people will call those quads because they have 4 wheels. Science is weird, we prefer tetra over quad. All right, what about 5? Now we're thinking about like 3-dimensional, or polygons with 5 sides. What do you call a polygon with 5 sides? A pentagon, so it's penta. All right, what do you call a polygon with 6 sides? Hexagon, so this would be hexa. What about 7 sides? This one's harder. Septa, septagon. Or in science, we use heptagon. Hepta is more commonly used over septa. Again, it's just one of these weird rules that we always stick with. All right, what about 8? Octa. So octagon. 9's tricky. 9 is nona. N-O-N-A. And then 10 is deca. So like I said, some of these don't always correspond to what we use in day-to-day life. We don't use quad. In science, we use tetra. We don't use septa. We use hepta. And nona and deca aren't commonly used, so we just need to remember nona is easy to remember, N for 9. All right, so these are the prefixes that are commonly used. There are actually ones going up to, I believe, 15, but I just want you to know 1 through 10. Those are the more common ones that you'll see in science. All right, I'll show you some examples of these. And I'm going to put an important note. The first note is do not use mono if it were to come first. And I'll show you what I mean by that with an example. My first example is CO2. Would I say monocarbon because there's only one carbon? No, because it comes first. So first I would start out just calling this carbon. Omit the mono for that. And then we've got 2 oxygens. So I would say di-ox. And then what's the suffix for CO2? Ide. So carbon dioxide. So there's a couple different things you need to remember. This IDE suffix is used anytime we're naming a covalent compound like this. And then you also need to remember the prefixes to indicate how many of each element that you have, right? So in this case, we've got 2 oxygens, therefore it's a dioxide, not a monooxide or anything like that. So carbon monoxide is very different than carbon dioxide. Yep?
We've got the OX here. Is that always what we expect it to be? Like the first syllable of whatever?
Yeah, essentially it's the first syllable. Sometimes this sounds unscientific, but it's whatever rolls off your tongue the best. So sometimes they'll lop off, let's say, a vowel. That way you don't have back-to-back vowels. Does that make any sense? Mm-hmm. Usually it's pretty intuitive when you're working through these. Like, this just doesn't flow well. I'm going to lop off a syllable. Yeah. All right. So let's do another one. I already kind of teased you with this. Let's go from the name to the molecule. So carbon monoxide. Again, we've got that IDE suffix indicating that it's covalent. You see how we didn't say monooxide? It's just monoxide. Again, it just flows better to say it that way. So we've got mono as our prefix here, but the ox in there indicates that it's oxygen. So what would the formula be for this? CO, exactly. So 1 carbon, 1 oxygen. We did need to include mono for the oxygen because it wasn't first in the name, therefore we include it. These are radically different. Did I talk about this before and tell you to get CO detectors? I can't remember if I did. But yeah, carbon dioxide, if you inhale a lot of it, your muscles will start burning, you'll start getting dizzy and lightheaded. It's pretty easy to tell when you're getting poisoned by CO2, therefore you can escape a building. CO, on the other hand, when you breathe it in, you can't tell, you'll just pass out and die. That's why we need CO detectors in all of our homes. So if you go home tonight, it might be worth checking. All right, let's try another one. N2O4. So it looks like we have 2 nitrogens. So how should we name the first part of this? Dinitrogen. We do need a prefix because it's not mono. We're not going to change the suffix at all for the first half. It's just the prefix plus the full element name, so dinitrogen. And then we need to include the last part of the name. So what would the last part be? Tetraoxide, exactly. So just like before, we've got tetra first. Then we've got the IDE suffix, and then the ox in there implies that it's oxygen. Let's try a few more. Let's do P4S3. So first half would be what? Be tetraphosphorus. So we do need prefixes in these two situations because they're not mono. All right, and then the last half, what does S stand for? Sulfur. All right, we've got 3 of them. So this would be tetraphosphorus. Tri means we have 3. Sul for sulfur. And then we want to have the IDE suffix. Does that make sense? And like I said, try to go with the one that flows off your tongue the best. It doesn't sound that right to say trisulfuride, but it makes a lot more sense to say trisulfide. So lop off the most appropriate last syllable and then replace that with the IDE, and it sounds a lot better. All right, let's do one more. Let's do PF5. What would this one be? Check with your neighbor and see if you agree. See a show of thumbs. Who feels confident with their answer? Thumbs down if you're not. Sideways thumb, it's like, maybe I'm off by a syllable or so. All right, so let's start. Is it monophosphorus? No, we don't include mono, it'd just be phosphorus. All right, what comes next? We've got 5 of F's. So it would be penta to indicate the 5. And what does F stand for? Fluorine. So what would the most appropriate suffix be? So, would I say fluorinide? Fluoride, exactly. Pentafluoride. So IDE as our suffix and penta for our prefix. Does that make more sense? So your next pod that's due Thursday is just practicing a lot more of this naming, but try not to overthink it. It's really easy to do that and to goof it up that way. All right, ionic bonds are a bit more complicated in terms of their naming. These are nice and easy. So let's kind of switch gears and look at ionic bonds. And of course, my internet is down. Just one second.
Welcome to Dogs Teaching Chemistry. Our first lesson is chemical bonding.
A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by 2 atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching, and we'll see you guys next time.
I don't know why those videos make me so happy, but I figured I'd share. All right. So like I said, a covalent bond is pretty easy to remember. By the co in it, that means it's a sharing of electrons. Ionic is different. That's where there's essentially a transfer of electrons. And when we thought about covalent bonds, we said that those normally occur between 2 nonmetals that share electrons, right? Ionic bonds, on the other hand, are different. It's often between a metal and a nonmetal. So often between a metal and a nonmetal. So if we look at the periodic table, typically the metals are thought to be on the far left-hand side, right? Including the transition metal block in the middle. And then the nonmetals are shown in blue. What do we call these kind of light yellow section? Metalloids. So really when we're looking at ionic bonds, we're looking at a bond between one of the atoms highlighted in blue and some sort of metal on the left-hand side of the periodic table. All right, so let's take a look at a classic example here. So in this example, we've got sodium. How many valence electrons does sodium have if we look at the periodic table? So group 1 must have 1 valence electron. And then we've got chlorine over here. Chlorine normally has 7. And if we think about chlorine, chlorine's really unhappy because it doesn't have an octet. It wants to find some sort of electron to either share or take so that it has an octet. And in this case, sodium says, I also don't have an octet. In fact, I would rather just give up this electron and give it away. That way I don't have to deal with it. So instead what happens is during this reaction, chlorine can take an electron immediately from sodium. And when sodium loses an electron, what charge will it have? Will it be positive or negative? Positive, exactly. So this is referred to as a cation. And then chlorine now has that extra electron that it took from sodium, therefore it must be negative, and this is an anion. And really what an ionic bond is the attraction between that positive charge and the negative charge. Opposite charges attract. So an ionic bond is the attraction between a cation and anion. All right, these reactions can actually be pretty powerful, so I wanted to show you a brief video of what this actually looks like in practice. Let's see if I can get this open.
Order on this sodium metal to activate. And we should see a pretty brilliant
Do you want to flip the lights?
reaction once I activate it. So I'm just trying to drop some water with a pipette to start the reaction.
So he's got chlorine gas in there and sodium metal.
There it is. And that white smoke you see is sodium chloride solid, the colloid. And so that white smoke is the presence of sodium chloride that we made.
All right.
And as at this
Does anybody know what sodium chloride is more commonly referred to as? Table salt. So essentially this smoke he made is super hot table salt. It's essentially just floating around in there, and then it will settle down. And if you were to look at the residue left behind, it would look just like the table salt that you would use in your kitchen, just really, really fine table salt, not the big grains. Yep.
We often see these kind of ionic bonds in solution.
Yep.
Do they look especially strange when they're solid, or?
So we'll talk about the difference between ionic bonds as a solid versus ionic compounds that are in solution. They are different from one another. But yeah, that's a good question. You mind flipping the lights? All right, so let's go back and define things in a bit more detail. Oops. So the first thing I wanted to bring up was an ion. And an ion is an atom or a molecule with a charge. Doesn't matter which charge it has. An ion can be positive or it can be negative. Doesn't matter, an ion's an ion. It just means it has more electrons than normal or fewer electrons than normal. All right? Like I said, if it has a positive charge, whoop, is that a cation or an anion? Cation. Versus a negative charge would be an anion. These are easy to flip-flop. So what I always tell people to remember is a cation with a positive charge, right? The T in cation kind of looks like a positive charge, so easy to remember that way. Conversely, some people remember anion has an AN, so N meaning negative, but then that's confusing because there's also an N here. I normally just use the T as a positive as a big clue there. All right, so those are important terms that we're going to use. An ionic bond, like I said, is always the attraction between a cation and an anion. So let's go back and practice something that was on our first exam. I'm going to give you an element, and we're going to fill out our tables. And down here, I'm going to put proton in this column. I'll do neutrons over here. I'll do electrons. Sorry. And then I'll do a charge here, and then I'll ask, is it positive or minus over there? Or actually, let me rephrase this. I'm going to change this to cation or anion. All right, so the first one we've got is sodium. How many protons does sodium always have, regardless of the isotope that we're talking about? 11. So it always has 11. So down here I'd say, well, sodium across the board is going to be 11. What about chlorine? 17. So number of protons always equals the atomic number. Now let's jump to neutrons. We know that the mass number, meaning the number in the top left-hand corner, is the number of protons plus neutrons. So all we need to do is subtract 11 from 23. And that would give us 12 neutrons. Same thing down here. 11 from 23 is 12. All right, what about the last one for chlorine? How many neutrons will it have if it's chlorine 35? 18. Hopefully everybody can do subtraction. All right, now the trickier one. First one, we've got sodium 23 with no charge, so it's just plain sodium. How many electrons will it have? 11. Going to cancel out the number of protons, therefore it's neutral. All right, sodium 1 plus right below it. How many electrons will that have? 10, right? It implies that it lost a negative charge, that's why it's positive. So it'd be 10. And then chlorine 1 negative, how many will it have? Must have 18, right? It has to have one more electron than protons, giving it a -1 charge. So there'd be 18 here. All right, now we need to do charge. We said originally sodium has a charge of 0. Sodium over here in the top right-hand corner says 1 plus. On the other side, it says 1 negative. You can do -1. I'm not picky about that. Some chemistry instructors are. Normally in chemistry, we show the number of the charge and then the sign after. Doesn't really matter too much in my opinion, though. All right, so the top one, is that a cation or anion? Or neither? I'd say neither. It doesn't have a charge. All right, what about sodium 1 plus? Cation. And like I said, that T in there looks a lot like a plus sign. And that must mean that chlorine down here must be an anion. Whoop. All right, so that's where I think we're going to stop today. On Thursday, when we come back, we'll look at naming ionic compounds because they follow a different set of rules. Remember to drop off your problem of the day, too, if you want points.